Now, in the previous example, we saw how 3-methyl were donating more electrons to the center carbon than the other two. So if I make a little change and say that in the previous example, I had this, and what I'm going to do is I'm going to remove this R and I'll get CH3, C, CH3 and a positive charge here. So this is what I'm going to do in this question now. So what we have here is 3 examples where R is being removed. That is, the alkyl group is removed from the previous question. The R group is removed, and we have another question here for you. If we remove the R, the C becomes positively charged. And now, while we are doing this question to see the stability of the carbocation, because whenever carbon with a positive charge, we know it is known as a carbocation. So we want to see which carbon is the most stable carbocation here. So you can see that if this has a positive, you can see that if this carbon has a positive charge here, then we know that these 3-methyl are giving negative charge to this, negative charged, or we can say they are donating electrons to it and making themselves delta positive, and the middle one, this one, electron rich. So they're making it more stable. Being electron rich will lead to a balancing of the positive charge that was already present because of the loss of alkyl group. So we can see that since the first one has more CH3 group attached to it than these two options which are already present to us, thus we can say that the first one, I'll mark it here for you, and the second one and the third one. So this one, the first one, will have more stability as compared to the rest of the two. And we can say, if we compare the stability of carbocation, which can be easily deduced by our plus I effect of the methyl group present, and we can say that 1 is greater than 2 is greater than 3. Also, I'll tell you another thing here is that since there are 3 carbon attached to this, this is a 3-degree carbon. And 3-degree carbon, or the 3-degree carbocation, is the most stable. So if I ask you the stability of carbocations, we can say that the 3-degree carbocation is greater than the 2-degree carbocation is greater than the 1st-degree carbocation. Moving on, the next example is on the basis of oxidation state. Now, oxidation state. What we know about oxidation state is that we gain any compound, for example, Fe3 plus here or Fe2 plus here, we can say that the more electrons they lose, the more positive charge they gain. So we know that this has lost more electrons as compared to the other one, that is this. So we can we not say that this is more electron rich as compared to this one, the first one, because more electron rich because less electron were removed. Less electrons were removed. As simple as that. So this has less elect. The first one, I'll mark it here for you. The first one, Fe3 plus, has less electrons as compared to this one, Fe2 plus. So we can deduce that minus I effect, which is the withdrawing of electron density, is more for that iron compound, that oxidation state, which is greater, because you can see that since this Fe3 plus has less electrons, so it will want electrons more and more, and thus the minus I effect, the minus I effect of greater oxidation state. Now I'm generalizing it and I'm saying greater oxidation state, since 3 plus, 3 plus is greater than 2 plus, so greater oxidation state is more. So I've made a general statement here that the minus I effect, what is the general statement that we have deduced? That the minus I effect of the greater oxidation state is more. So the more the oxidation state, the more is the minus I effect. That is, minus I effect, we'll write it here, that the minus I effect is the electron withdrawing factor. So it will withdraw more electron withdrawing factor. So this is it. And if I want to give you the last one, I can say this. So Fe3 plus greater than Fe2 plus. What is this? The minus I effect.